Hi, this is me, and I have a real problem with this section. I'm going to go straight to this. Okay, here's the thing. Wheels and friction are complicated. Okay, there's not an easier way to say it. When you look at a random wheel, or a random wheel, we'll just say it like this, a spool. Just looking at the spool rolling, you can't always tell if the friction is pointing this way or if the friction is pointing this way. If you've just got, like, say, a spool, like with a thing in the center, like a little spool. There you go. Now, on a car, this is a car that has tires. Okay, for the most part, and again, we're assuming the cow is spherical. If the wheel is free to roll, like if it's just loose, we assume there's no friction. Because it's just, there is friction, but it's considered low enough that it's nothing compared to everything else in the car that's happening. So the friction is less than whatever matters. So basically you can do all this math and then you get the car is going, an acceleration of 96 meters per second squared, and then you put the friction on that back tire and it becomes 95.993 meters per second squared. And if you really get into race car driving, maybe that matters. For the purposes of physics 1 or even in dynamics, we don't care. Okay, so it depends on if it's front wheel drive, rear wheel drive, but usually if you have a tire, a lot of times one of the wheels doesn't roll. So I'm going to just consider this a front wheel tire. I think we'll just do it that way. So let's pretend the engine is explicitly turning this wheel. Okay? So you think this wheel is going this way, right? So if the wheel is going this way, the question is, which direction is friction going? And a lot of people are like, well, the car is going this way, therefore friction is going this way. But that's not correct, because in fact the only thing that moves the car forward is friction. And if you don't believe me, try to drive your car in the snow. The only way that this car moves is if the frictional motion on that tire, or the frictional force, frictional whatever on that car wheel, the friction has to go this way for the car to move. And think about it. If it slips, it's going to slip, again, this direction. And the friction is in the direction that's trying to prevent it from slipping. Okay? Does that make sense? So this is really, really, really important because it's going to come up. And I can't account for all the questions that are everywhere, but you need to start thinking about this although things seem super easy until they don't. Well, I guess that's it. Yeah, things seem super easy until they don't. And then you're like, wait, what just happened? How come friction is going forward if my motion is going forward? And it's because if I do the sum of the forces on this car, there's like some forces in the y direction. The only force in the x direction on this car is the frictional force caused by that tire. And I guess you could say there's two of them, but twice the friction of the force. And that's equal to the mass of the car times the acceleration of the car. So the only reason that car is moving forward is because of the friction. So if you have the friction arrow drawing to the left, that means the car is going backwards. And you're like, well, the car can't going backwards if the wheel is going forward. Absolutely. That's how we know that the car is going backwards. Yeah, okay. I'm just going to leave it at that for the moment. Now, this is where, so you either have to believe me or you have to convince yourself, but this is actually legit important to think about and believe in yourself, believe in the power of friction that moves your car, because if your tires are bald, you don't go anywhere, right? If it's icy, you don't go anywhere because there's no friction. So therefore, friction is literally the only thing that moves your car forward. You're like, there's an engine that moves it, but how does the engine move it? Because it creates friction with the ground, okay? Friction makes your car go forward. Now, in this picture, they have friction pointing the opposite direction, which is the only way I can come up with this, because they say it's the two students push a stalled car, and I'm going to straight up say that unless the wheel is locked, this is not going to be pushing backwards. So this is only assuming you have the brake on, which is kind of a horrible thing to do to these two guys who are trying really, really hard to push your car. Now notice that there's no friction on this back wheel because the back wheel is free to roll. So apparently this lady has her foot on the brake while they're trying to push the car. Got it? Got it? Got it? Okay. I also don't like drawing this weight arrow down here because it looks like it's attached to the wheel, and the weight really is just the weight of the whole car. And I like to draw it near the center of mass. So the only reason that you would have frictional force on that chick's car is because she's slamming the brake while they're trying to push it. So that's fun. Okay. Now, this tow truck. I don't know what's happened to the back wheel. We've apparently locked the back wheel. I don't know why we've locked the back wheel. I have no idea what's going on with this tow truck that it is towing it like that. But if I was going to be drawing, now maybe they're just simplifying it for you, but it really bothers me. So I'm going to draw this car the way I think it should be drawn because I'm a pretty princess. So here's my car, and it's on a platform. And let's just say it looks like it's, don't they usually chain him like on the bumper? Chain to the bumper. Okay, for simplicity, this is what my car looks like. Okay, this is the tow truck that it's on. Okay, see what's going on now? Okay, so there's my car tied to the tow truck. So you have your weight of the car, you have your normal force, and you're like, wait, I thought the normal force was supposed to be perpendicular. It is. It's perpendicular to how the tire touches the ground. Oh, because we're now doing the free body diagram of the car and tire system. Okay, so we're doing the free body diagram of the car and tire system. Therefore, this is normal to where the tire is hitting. So there's the normal to the ground. I guess I could move this over a little bit. So there's this normal to the ground. And then there's also going to be a normal to the truck because it's sitting on the truck. I don't know why they don't draw it sitting on the truck. And then there's the tension for the tow truck. I don't think there's any friction because I'm pretty sure that the people who run tow trucks are smart enough to turn off all the emergency brakes, right? So I have no idea what they're doing here. I don't know what this tow truck dude is thinking, why there's friction. Like I said, I guess in a quantum physics level there's friction, but no, just no. I mean, it's just no. So I'm not going to worry about it. And maybe one day I'll have to come back and redo this video and be like, oh, I was so wrong. Physicists make up stuff and engineers don't care. But for the purposes of simplicity, I'm going to say that I am going to die on this hill, apparently, that you need to have a normal force on that truck because it is sitting on the truck. Now, the reason they probably didn't do it is because mathematically you can't solve it yet because you don't have the skills. But if we're going to draw a free body diagram, we need to be honest about what that free body diagram looks like. Okay, so let's see if I have any more problems with their other free body diagrams. Okay, this guy is apparently hitting a ball in a car for some reason. A basketball player pushes on a basketball to make a pass. The same player exerts an identical force on a stalled SUV and produces far less acceleration. Why? Because he's pushing on the car. It was like he's still pushing a basketball. No, because the car is not moving. The free body diagrams for both objects are the same. For what objects? For him or for the car? No, doggy. So I don't like this picture either. This doesn't make any sense. Okay, let's do the first one. We have dude. Here's dude. We have ball. Ball and dude look the same. We'll give him some hair. now it's a girl. Girl is pushing ball. Okay, so girl has a weight and a normal force with the ground. And she is, let's say, in the process of pushing ball to where she's still holding the ball. Because once she lets go, there's no more force on the ball. Okay, so right now, if I'm drawing the free body diagram for the ball, girl is pushing on ball, but ball is pushing, whoa, I keep erasing stuff. Let me try this again. This is going to be hard to draw. Okay, so here's girl, she's pushing the ball. Yay! What do we do about this? Because I'm clearly flummoxing it just by trying to talk about it. There's something going on here. We'll say the ball also has a weight. Weight of ball, weight of girl. Okay, what's going on there? Okay, if we separate them, so if we just draw the free body diagram of ball and girl, that's what it looks like. Now, if we separate them, actually, that's what I'm going to do. If I separate them like, whoa, dang it. Okay, honk, honk. Okay, I'm now going to separate them. And I'm going to expose the internal forces. I don't know why her hand came off with that. I'm going to expose the internal forces between girl and ball. So ball is getting pushed on by girl. And in return, the ball is pushing back on the girl. Now, why isn't the girl going forward? Well, because probably she's wearing shoes that are preventing her from going forward. So this would actually be an external force even to the whole system. So she has some kind of friction on her shoes that keep her from toppling over whenever she gets a pushback from that ball. So when she pushes the ball pushes back. So at t equals 0, this is what the free body diagram looks like. Okay, and the idea is, this is actually Newton's third law, which is for each action there's an equal and opposite reaction, so this is kind of weird to talk about it here. But if we put this on top, do you see how those two arrows cancel out? That's because they're equal and opposite. She pushes on the ball, or you could say the ball pushes back on her. Really, they're both true. Both things are equally happening. But now, if I look at this again at t equals, 0.0001, okay? So if t equals, I'll make it, whoa, I was trying to make it easier to read. So now if I change it to t equals 0.01, she's here, and the ball is here. There is no more force between them. So although she gave that ball an initial force and an initial acceleration, initial blah, 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 now, so there is some kind of acceleration on the ball in the x direction that's not 0. But here, now the acceleration on the ball is 0 again. It's going a constant speed. It doesn't get faster just because she pushed on it really, really hard. The ball doesn't keep getting faster and faster and faster in that direction. Now the acceleration of the ball in the y direction continues to be negative 9.81 meters per second squared, just like it was over here. Acceleration of the ball in the y direction is negative 9.81 meters per second squared. This is super duper, duper duper, duper duper important. Once she doesn't touch the ball anymore, she is no longer applying that force and getting into like, well, the impulse of how long she applies that force and da-da-da-da-da. You could do all kinds of math with that. But from a free body diagram perspective, I have no idea what they were trying to draw. This is what I would draw, and this is how I would solve problems with it. So maybe you can do weird things with those other drawings, but I don't get it. Now, what was she doing with a truck? She was pushing on a truck. Free body diagrams are the same. Not really. Okay. So let's try this with the truck. So now for some reason this chick is pushing a truck. And we all know how good I am at drawing trucks. Okay. Truck. Oops. Let's do this truck. 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 And chick pushing truck. Okay, so if this is system of chick pushing truck, we have normal force of chick, weight of chick, girl, person, weight of truck. We have the normal force on the back tire. We have the normal force, I didn't actually draw it touching. Maybe she's so strong she lifted part of the car above. Let's pretend that didn't happen. The normal force of the second tire. And if the tires are rolling freely, there is no force on the tires. So if you want her to be pushing on the truck cannot move forward right now, the way we have this drawn. So you have to think, what is going to make this truck move forward? There has to be some kind of force in this direction to get a non-zero acceleration. So the only way you can get a non-zero acceleration is if there's some kind of friction, and since the truck is apparently not working, the only way that we can get an acceleration is from the friction on her shoes. So now the friction on her shoes is overcoming so some of the forces in the x direction are her friction needs to equal, really for the purposes of what we're doing here, it's the acceleration of the system, because she's like leaning forward with it. So we think like the center of mass of the system is, you know, like here-ish. So what is the acceleration of this point? It's something like, and I'm really doing a lot of hand waving here, but you're just going to have to deal, is going to be her, well, I put her weight plus the truck's weight divided by 9.81 to get it to mass times the acceleration of the system. So that's the acceleration of the system if, you know, she keeps successfully pushing like that. I don't really know what they're trying to draw over here. I think they're just trying to say if somebody pushes on a ball, they push it harder than if they push faster than if they push it on a truck, and in which case they should say that, but their free body diagrams are nonsense. So there you go. But I hope that kind of makes sense. So because of their mass, weight of the girl, weight of the truck, so that's their total weight divided by 9.81 to get mass, is the acceleration in the x direction at this exact moment in time. And that's the other really important part to talk about. At this exact moment in time. If she lets go, then the car will, in theory, continue at constant velocity for all eternity in a frictionless world. Yeah. So it's pretty something. Make sense? I mean, and it's okay if you say, no, that doesn't make any sense. But I'm letting you know that if you read this book and you're like, what is this? My answer is, I don't know either. I think it's garbage. But it's free. So, I mean, okay, it's also entirely possible that I'm a snarky engineering professor teaching physics, and I have like a very specific reason that I'm learning it, and it's not the same reason that a physics person learns it. What acceleration can a person produce when pushing a lawnmower? Okay, so this one's easy compared to some of the other stuff, because it's just saying, I'm giving you the net force, I'm not making you draw a free body diagram. So the net force on a lawnmower is 51 meters to the right. So the net force in the x direction is 51 meters to the right, so that's mass times acceleration. In the x direction, what is the mass of a mower? The mass of the mower, and we'll just assume the mower is, it doesn't matter. We're just going to go with it. The mass of the mower is 24, so the unknown acceleration, okay, we'll get there eventually. 51 divided by 24, oops, 24 with the dot. So about 2.125a, x equals 12 point, I already forgot. Oh, 2.12.5. 2, hi puppy. No, I don't need love. I mean, I do need love right now because I don't like doing this. Meters per second squared. Okay, so that's because they already gave you the net, so you're good to go. Okay, that's what they got. Okay, Okay, the car shown in this figure that I probably already erased. In F13, figure 13. Where is figure 13? I'm not very good at paying attention to things. This is figure 10. Oh, figure 13 must be down here. Oh, it's below me. Okay. If it's moving at a constant speed, I don't even need to look at the picture. Which is bigger, friction or drag? I mean, if velocity is constant, friction, if the only two things going on it are friction and drag, if the sum of the forces is constant speed, that means it's 0, so that means friction equals drag. So they're equal. That's the only way it can happen. They have to be the same. Drag and friction have to be the exact same if it's moving a constant speed. Let's make sure that physics doesn't do things weird. Okay, forces are equal. Beautiful. All right, the same car is now accelerating to the right, which is bigger. I have hair on my screen. Which is bigger forces. I'm sorry that this video is longer than I wanted it to be. It's just, this is really, really, really important. Okay, so if it's accelerating to the right, so mass times acceleration, and we know that acceleration, I don't mean to draw it like it's an arrow, but it's accelerating to the right, then if it's friction minus drag, then this needs to be positive, so that this is positive, so it's going in the right, correct direction. So friction has to be bigger than drag. Because if drag was bigger, I mean, that also wouldn't make sense, because drag is like, you know, you don't go negative distance with drag. That's then becomes just something else. Okay, so friction is larger than drag. Okay, what rocket thrust accelerates this sled? Oh my. Interesting. Okay. So we're just going to, since I am a rule follower, this is the picture been given to me, and I'm going to solve this picture given to me, and it's going to be fine. You know what? I'm not even going to solve this picture. You can read it. It's a picture. You add up stuff. You subtract F equals ma. You calculate friction. You get divided by the mass. What did they do here? Okay, now I do have to figure it out, because what they're doing doesn't make any sense. Okay. So the sled's initial acceleration, so it's asked to calculate the thrust. So there's 4 thrusts going forward. See, I was going to be all cool and skip it, but now I'm confused. 4 thrusts minus a friction equals mass times acceleration in the x direction. So the sum of, I always do this. Sum of the forces in the x direction is 4 thrusts minus friction equals mass times acceleration. So 4 thrusts minus, and they tell us what friction is. Friction is 650, is that in newtons? Yeah. Minus 650 equals mass 2100, and its acceleration is 49 meters per second. Everything's in meters, seconds, kilograms. Okay, I already forgot what the number was though. 49. I just want to make sure I get the same answer they got, because now I'm weirded out. Very distrustful. But that makes you a good scientist. 2100 minus 40, times 49. Plus 650. Look at me doing algebra like nobody's business, but not calculating like nobody's business. Oh my goodness. So that's 103,550. 4t equals 103,550. So t equals that divided by 4. Please give me the same stupid number. 28,887. And this is going to be in newtons, so I could maybe say 25.9 kilonewtons. Is that what they got? Well, who the hell knows what that is? Well, that's just calculating the total thrust. And they said it's 1.0 with 5 zeros. 1, 2, 3, 4, 5. So basically 100,000 for all 4 of them. Come on, girl. Oh yeah, for all four of them, I basically got 100,000, except I included more digits. All right, well, I mean, it's just rockets. It's not like all those digits matter or anything. Can you hear the sarcasm? Okay. Please tell me we're almost done. Component form. Oh, I was already talking about this. Yes, so this is basically, we're going to do the same thing in two different directions, but I'm going to go ahead and put this in another video because this one has gone on way, way, way longer than it needed to.